Good morning, champ. Time to put all your multivariable skills together. We've learned about partial derivatives, Jacobians, and Hessians, and now we'll use them to approximate complicated functions with simple polynomials. That's what the multivariable Taylor polynomial does. It gives us a smooth polynomial clone of a function near a chosen point. Just like in single variable calculus, it's a powerful way to locally linearize or curve fit a function. Let's start with the idea. In single variable calculus, the Taylor expansion around x naught is f of x approximately equals f of x naught plus f prime of x naught times open parenthesis x minus x naught close parenthesis plus 1/2 f double prime of x naught times open parenthesis x minus x naught close parenthesis squared, and so on. For a function of two variables, f of x and y, we do the same thing using partial derivatives. Now we capture how the surface changes in both the x direction and the y direction. The first order Taylor polynomial, also called the linearization, of f at the point x naught. Y naught is f of x. Y approximately equals f of x naught. Y naught plus f sub x times open parenthesis x minus x naught close parenthesis plus f sub y times open parenthesis y minus y naught close parenthesis. That's the equation of the tangent plane. It matches the function's value and slope at that point. To add curvature, we use second partial derivatives. The quadratic, or second order, Taylor polynomial is f of x. Y approximately equals f of x naught. Y naught plus f sub x times open parenthesis x minus x naught close parenthesis plus f sub y times open parenthesis y minus y naught close parenthesis plus 1/2 times open bracket f sub xx times open parenthesis x minus x naught close parenthesis squared plus 2 f sub xy times open parenthesis x minus x naught close parenthesis times open parenthesis y minus y naught close parenthesis plus f sub y y times open parenthesis y minus y naught close parenthesis squared close bracket. That's the quadratic Taylor surface. It captures the bending of the function near the point. We can write this neatly using matrices. Define the gradient vector as nabla f equals bracket f sub x, f sub y bracket transpose, and the Hessian matrix as a 2x2 matrix with entries f sub x minus x, f sub x minus y, f sub y minus x, and f sub y minus y. Let H be the column vector bracket x minus x naught, y minus y naught bracket. Then the second order Taylor approximation is f of x naught plus h approximately equals f of x naught plus the gradient transpose times h plus 1/2 h transpose HFH. Now let's see a concrete example. Take f of x, y equals x squared plus xy plus y squared and approximate it near the point 1, 2. Compute the derivatives. F sub x equals 2x plus y and f sub y equals x plus 2y. The second derivatives are f sub x minus x equals 2, f sub y minus y equals 2, and f sub x minus y equals 1. At the point 1, 2, f of 1, 2 equals 7. The gradient is bracket 4, 5 bracket transpose, and the Hessian is bracket 2, 1, 1, 2 bracket bracket. Substitute these into the formula, and we get f of xy approximately equals 7 plus 4 times open parenthesis x minus 1 close parenthesis plus 5 times open parenthesis y minus 2 close parenthesis plus 1/2 times open bracket x minus 1 y minus 2 close bracket times the Hessian matrix times the column vector bracket x minus 1 y minus 2 bracket. That's our second order Taylor polynomial at the point 1, 2. If you plot it, the paraboloid fits the original surface almost perfectly near that point. You can go even further. Geometrically, the first term f of x naught gives the function's value at the point. The gradient term gives the slope. That's the tangent plane. And the Hessian term adds curvature, bending the plane into a paraboloid. Higher order terms refine that shape even more. Let's summarize. 1. The first order Taylor polynomial gives the tangent plane. 2. The second order adds curvature through the Hessian matrix. 3. In matrix form, it's elegant, compact, and easy to generalize. And 4. It's the foundation for optimization, numerical analysis, and even machine learning, where we approximate complex functions with simple quadratic surfaces. So, multivariable Taylor polynomials are your mathematical zoom lens. They capture slope, curvature, and local shape, turning calculus into geometry.